Want to start the recording? Are we going? Okay, so thank you everyone for coming. Our first talk is Evelyn Legendre from Toulouse, and she's going to be telling us about valuative stability for polarized varieties.
Yes, so hi everyone, thank you for the invitation. So it's a joint work with Rui Dervan within Cambridge. So that we have done last year during the first lockdown. So it was very, that's nice. Okay, so I will talk. I will talk about case stability and valuative stability. So in the last few years, there's been a lot of progress in understanding case stability. I don't know if you are keeping track of this, but actually one of the reasons why I was interested in this is this particular case of the Yao-Tian-Donaldson conjecture, which says that there exists. Oops, we should. There exists Keller-Einstein metric. In Keller-Einstein metric omega in the first rank class of manifold. Maybe I can do that. If and only if the manifold is, the manifold of variety with this polarization is a case stable. Case stable. Okay. And so that in this case, that was proved by Chen Donaldson son, but, and also other people have given different proof since then. And actually, from the point of view of I will look, it's just from the algebraic side of the picture. So the algebraic side of the picture is this one, of course. And the theorem I would like to talk about today is about another way to define this case stability, which has been given by Fujita. Okay, so in this situation, so of course there's some assumption on the variety. It has been proved by Fujita that it is that this variety is case stable, a final variety is case stable if and only if it's valuative case stable. Sorry, relatively stable. And so using this and using this stability, but well, within the same years, there are some other people, algebraic geometers like Chili, Chen Yu, Liu, Fujita. Fujita already gave it his name. They have developed other ways to address this question and describe the case stability condition. And one of the reasons why it was why they were able to do that is that they use in some very important way the minimal model program, and so there's been a lot of nice thing has been done, and in particular that these different notions of stabilities allows us to study the moduli space of final manifold and Keller-Einstein final manifold. Okay. So with Rui, so we wondered if to what extent we will be able to define the stability, especially the valuative stability for generalized polarized varieties. So even if the conjecture is not proved or whatever, we were expecting that some complication would come, and there was some complication, but actually it was a very successful project in some sense, because we understood what valuative stability could be for a generalized polarized manifold, and this is what I want to talk about today. So the question we asked ourselves was, the first one was simply, does the Fujita valuative stability makes sense for general polarized varieties. So for this question, the answer is yes. It makes sense. Well, we need some condition on the variety. For example, so it has to the anti-canonical bundle must be Q Cartier and stuff like that. But well, I think we are satisfied by the answer. So in that case, it works well. The other question which is very natural, is that is there an equivalence between valuative stability and K-stability? So could we extend the Fujita's result in our case? And so, well, I would say that the general answer is, well, essentially no. Essentially no. But again, if we add some condition, like if we will be talking about integral K-stability, then there is an equivalence between valuative stability and integral K-stability. So maybe I can say that, I can write it, but valuative stability corresponds to integral K-stability. So I will define in detail what I mean by these notions. Well, for integral, there will be an integral manifold somewhere, or an integral, I say manifold variety, and I will define in details what I mean by valuative stability, and which is, well, essentially the Fujita's notion, but with a different numerical invariant. So maybe I should warn you, my background is in differential geometry, so this is why I really tend to use like manifold, but I'm thinking about varieties, so sorry. And that project was very good for me because it allowed me to learn a lot about these stuff. So, but I might be a little bit naive in some sense, in some explanation. Okay, so the plan of the talk is that first I will define what I mean by valuative stability. So in general, when, well, probably all know that, then when we talk about algebraic stability, any kind of stabilities, then there's a geometric or an algebraic situation, and there's a numerical invariant, right? And again, here's going to be also true, absolutely. Maybe I'll take that down. So here for the valuative stability, what the geometrical or algebraic object will be a valuation, actually a divisorial valuation, and the numerical invariant will be the beta invariant. Actually, it's not exactly the beta invariant of Fujita. It will be another, a variation or an extension of that invariant to our specific situation. So in the case of K-stability, then the geometrical or algebraic object is a test configuration. And then the numerical invariant is the Donaldson Futaki invariant. Maybe I can write names. For one, is the Donaldson Futaki invariant. Okay. And so what I plan to do for this talk is first take time to define all these notions. And then I would like to show that actually the two geometrical objects, the divisorial valuation and the test configuration, actually they are in correspondence in some way. So here I will add some condition on the test configuration, is that it's an integral test configuration. Okay. And the last part of the talk, I would like to show that actually the two numerical invariants match. Actually, they are the same. in this specific situation. So maybe maybe because that might take some time. So here it's very true, the notion of filtration. Okay, which has been developed by David Wittnestrom and Gabor Sekedi. And here, actually, here we will need to use some very non-trivial results using MMP in the special situation we are at. And so maybe I should say here I will need to add something on the divisorial evaluation. I will only look at dreamy ones. I will explain all this now. Okay. So let's start. So valuative stability, what I mean by that. So I take a polarized variety, normal, irreducible, reduced. Actually, secretly, I'm only thinking about smooth or orbifold stuff. So Q factorial, if you want. Actually, I will add some condition later. And F is a divisorial evaluation. Okay. So what does that mean? So I guess that everybody knows what's evaluation here. In case, just let me recall so that it means that there's a model, a birational model. So here it's birational. Okay. And F, a prime divisor in Y, so that F is prime, is a prime divisor. Okay. So with these objects, I will define the following. So here I'm following. Well, I mean, this project was essentially reading Fujita's paper and really realizing that actually we can extend it. So typically, all the notion here, at least I'm talking about, we are taking it from Fujita. So for all k an integer greater than 0 and x greater than or equal to 0, I will define the following space. So it looks like a global section. It will be, but it's not global section on x. It's global section over y of that thing. So this is equal to the global section over y of the pullback KL minus the integral part of x over f. Okay, so you can see that as global section of KL over y, or the pullback of all this over y, and that vanishes along f at the order given by that number. And so we see that thing as a subset of, as a subset, as lying in the global section of the pullback. And then this is, this can be completely identified with a global section of L over KL time over L, okay? So to define the beta invariant, I will need the volume, which I recall is defined as the lim sup of the dimension of that thing. You see, I hope you see it's big enough. And so maybe it's good to notice that this thing is necessarily smaller than n, which is actually the dimension of y. And it's also, of course, greater than or equal to 0. So the fact that it's bigger than the, it's smaller than n, the dimension of y, it comes from the fact that it's given by the Ithaca dimension of the embedding. So coming from L, or not the embedding, but the map given by L. Okay, so what do I want to say? Maybe a remark. I'm just recalling that when you have a line bundle like that, then L. So if L is ample, then the volume of L is just 1 over n tensorial. So this is just given by the intersection number n, so the usual volume. And also, if L is big, then actually it's then in that case this the volume is strictly positive, and actually this is one-to-one correspondence. Yes. Okay. So here for our purpose, and because we are working on we want to work on x, so we define the volume. We define that thing, the volume over x of Lxf. So actually that thing, it makes no sense, it's not defined, and so we define it as the volume over y. And actually one can prove it's not that it's very natural that actually does not depend on well, it's clear that it does not depend on the on y. Okay, and now because of that correspondence, we also define tau, which is the pseudo-effective threshold, and which is given as the supremum for which the difference of the bundle is big. Okay, and so you can see the volume as some function that goes to 0, and there's a very important theorem of Buxom, Favre, and Janssens, which says that this volume, as it is defined on the numerical class, actually it's a C1 function. Okay, that will be very important for us because in the beta invariant, actually we are using the derivative of the volume. Okay, and it is the part which was not in the Fujita's formula. Okay, so to define the beta invariant, which is just here actually, I still need to define some invariant, and I need to assume that kx and ky are q-carty actually, because I want to use the log discrepancy. So here it's the order of vanishing of ky minus sigma, the pullback of kx plus 1. Okay, and the other, there's another, there's mu here that I didn't define, which is an intersection number. Oh, and here's n minus 1. Okay, so so you see in this formula there's the volume of a ring, the integral of the volume of some big line bundle that going from an ample line bundle to something which will not be big anymore, so that goes to 0. So for example, I could replace these the threshold here by just plus infinity, and that would give the same one. Okay, so maybe one remark that I should say. So this is not obvious from the definition itself, but if you well compute this, if you use the integration by part in the case where you are on a Fano manifold and L is the anticanonical class, then actually the beta L as I define it upstairs, you can find that this is exactly the Fujita's invariant, beta invariant. And so this is this volume of L and minus 0 to tau. So tau LF, if you want, the volume of L minus XF dx. Okay, and so this is exactly the beta invariant of Legendre. Okay. Okay, and so that would be the numerical invariant appearing within valuative stability. So we would say that polarized variety is stable if for all dreamy divisorial evaluation, then this invariant is positive. Then that means stability. Okay, and so for this, I need to define this dreamy condition, which is here. I hope you see enough, big enough. So this is fine. So here it's written finitely generated. Okay, so and here this is a Z2 graded C algebra, and that will be very useful for us. That condition, which seems well, it's technical. Okay, it's technical. It can be seen as a technical condition, but it's important and useful for us because it allows us to define to first define the test configuration out of divisional evaluation, but also to compute and to make the numerical invariant match. Okay, so we will see. We'll talk a bit more about this condition. So maybe now I can state the theorem. Okay, so so let XL be a polarized variety. So, well, I mean, of course, irreducible, normal, reduced in case, and also with this condition, this condition, which maybe I should say that this is this condition that Kx and Ky are Q Cartier. It's well, it's of course true when X is smooth and Y is smooth, and are more generally Q factorial, so kind of default type. So in this condition, if you have a polarized variety that satisfies this, then we would say that well, we have this condition. I'll write it this way: beta f is greater than 0 for all dreamy divisor relative divisorial evaluation f over x if and only if x L is K stable. Well, we have also a statement with all kind of stability like semi-stable, uniform stable, blah, blah, blah. SK stable with respect to test configuration, with reduced and irreducible central fiber. I would recall right just after that what's very soon what's a test configuration. I took for granted that most of you would have heard of that before. So so this is what we call valuative stable. And this is what we call integrally stable. Okay, stable. Okay. So here, the fact that the central fiber is reduced and irreducible, so it means that it's an integral variety, and this is why it comes from. Okay, so this is so maybe I should say some comments about this. So by a very great result of Li, Liu, and Shu, Fano varieties are a Fano variety is k-stable if and only if it is integrally k-stable. Actually, we just have to take test configuration to test k-stability with test configuration having a reduced and irreducible central fiber. Okay. And so using this result, we see that our result is really extending the Fujitas one, because actually in the Fano case, you only have to test this integral k-stability. Okay, so this is very an extension of that case. However, we don't believe, I think I can say we on this, yes. We don't believe that we would be able to extend Fujita's result, in the sense that we don't believe that valuative stability is in one-to-one correspondence with case stability. Okay, it's not the same thing, it's simply an equivalent. And maybe to convince you of what we believe, I can talk to you a little bit about the toric case, even if I won't go very long in this. So this is the thing I was just saying. I should have shown you. So
sorry, I think Hamid has a question. Hamid, you've got your hand up.
Yeah, sorry. Just a question. In the usual case before your paper, also the assumption of dreamy can be dropped from Fujita's work.
Yes, actually, so Fujita proves that actually that you don't have to that it was valuative stable for dreamy, like if that the beta invariant is 0. So maybe I can go there. So what he proves is that you have this for all dreamy ones, if and only if you have this for all variables.
Great, but then there's a paper by Bloom and Xu that basically there's a corollary that says the assumption of dreamy can be dropped here.
Yes.
So from his work.
Yeah. Well, so I guess the question is that would it be true for us as well?
Yeah.
So so maybe the toric case could be helpful for this. I think it would.
Thank
you. But well, I must say actually that for me the dreamy condition is very mysterious, and that theorem of us was very well enlightening for me, because I think I understand more test configuration with reduced and irreducible central fiber than dreamy condition. Okay, and and for now, what I can say also is that in the proof we are really using the dreaminess condition in an essential way. But let's talk about the toric case. I think it could be maybe explaining something, maybe not. And please tell me if it doesn't answer. But so for a toric polarized Q factorial variety, we will call a divisor over X toric if its center, which lies in X, right, is fixed by a C star action in the torus we have at the beginning. Okay, do you see well enough? Okay. That bigger. Okay, and so these are a particular case of well, the divisorial evaluation. So maybe I should say divisor. Well, I should have said evaluation here, but anyway. And what we prove is that for all toric then evaluation f over x, we have it's stable. So beta the beta invariant of f is greater than or equal to 0 if and only if the theta k invariant is 0. Okay, so the proof is Fujita has a similar result, and the proof is an extension using some kind of measure on the boundary of the polytope. So it's a little bit more complicated, but it's completely related. Actually, we can write the beta invariant as the theta, the usual. So here, by theta k invariant, I mean the classical theta k invariant. If and only so beta is essentially what we can prove here. So maybe not red. So what we can prove actually is that this is some positive term plus plus the theta k invariant, essentially. Okay, and then actually we can also prove because in the compact case we can prove that it's the result I just mentioned. Okay, so now maybe you know, or maybe not, I don't know, that there exists a polarized toric surface. Okay, that I will just take XL, so whose theta k invariant is equal to 0. And but as a destabilizing test configuration. Destabilizing test configuration. So this implies that it's not stable, unstable if you want. Okay. And so this example is in the original paper of the Nelson on toric, on K stability and toric varieties. And so what does it tell us? So it means that this is valuative stable in the sense above, in a stronger sense actually, but because here we don't say that F is dreamy, okay? And but actually this is not K stable. So I don't know if it's answered the question, but this example actually make us believe that it's not well, even if it's in some kind of equivalent case, it makes us believe that it's not possible that we have an equivalence between valuative stability and K stability. Okay. Maybe on the positive side, there's an example of there's a result of Thibaut Delcroix, which says that actually for some spherical manifolds or varieties, sorry, if you're close enough, if you take an ample line bundle which is close enough to the anti-canonical bundle, then it's enough to test integral test configuration to test K stability. So in that situation, that's telling us that it will be enough, that valuative stability would be equivalent to K stability. Okay. So maybe I can continue. So I will recall briefly test configuration. I imagine that most of you have heard of it. That construction before, which is due to Tian and Hansen, and I've been in the center of interest of many people since. So let me recall. So I would first define a test configuration. So a test configuration over XL is a pair, actually, where X is a normal variety, and a C star action. Okay, and L is a linear, so C star GM, whatever you want. C star linearized line bundle over curly X, and there's a map which is equivalent and flat. So equivalent with respect to the action we have, and with respect to the standard action on C. Okay, and with these following conditions, so there exists a number or an integer such that for all over every fiber outside the zero section, you can identify the fiber is isomorphic to X, and the restriction of the line bundle over that fiber is actually isomorphic, like equivalently isomorphic to L power R. So typically for the purpose of the talk, to simplify things, I will assume in my statement that R is equal to 1, just to simplify. And but it would not be enough to consider everything, and it's really needed. And you also ask L to be relatively ample, which of course comes for free over the generic fibers, but for the central fiber, it's not. It's not. So about that, the central fiber is the fiber over 0. Okay, and so because the C star action over C fixes 0, then it means that you get an action C star over that variety. And so typically, so the usual drawing that you see, the usual picture is that you imagine here that you have E1C if you want, which is just C, right? And then the usual fiber are just written this way, and then the central fiber could be very, very complicated with a lot of piece actually in it. Okay, and so saying that that it's integral, what we assume is that so maybe a definition. So we would say that the test configuration is integral if X0, so the central fiber, is integral. So which means reduced and irreducible. Okay. Yes. So that's a strong, like that's a strong condition to be integral for a test configuration. But there exists some example of integral test configuration that are not trivial. And many example, like for example, if the central fiber is smooth, then it's integral. Okay, now the Donaldson and Fittek invariant, so the numerical invariant associated to that geometric object, and that will be the numerical invariant we are defining the case stability, comes from the action. So it's so we get a C star action over the central fiber, right? As I was explaining, and actually because not only on the it's also on the line bundle. Okay, so from this you have a weight WK. So maybe I can write the K will always be just the exponent of the relatively ample bundle. W key is the weight. Okay, so this is a weight over a one-dimensional space, which is given by which is actually the section of actually it's one-dimensional, so I take the wedge t time, where dk is the dimension. So here maybe I can just finish the line. 0, k, l0, and here is the dimension. L0. K again. Okay. So, so this is one-dimensional space. So the weight is just an integer, and then what we want to, and then the non-symplectic invariant is essentially the sign of this weight the asymptotic in the asymptotic expansion. Okay, so we have an asymptotic expansion which comes from like equivalent Riemann-Roch theorem. That goes as follows. And then we have the dimension. Oh, here it's -1. Okay, and -2. And then the Donaldson-Fidaki invariant is of the test configuration is B0A1 minus B1A0, all that divided by A0. Okay. And so, as usual, we say that KL is K semi-stable, XL is K semi-stable if it's non-negative for all test configuration, curly X, curly L over XL, and it's K stable if it's K semi-stable, and that the Donaldson-Fidaki is 0 if and only if it's a product type test configuration. Okay, so some trivial case. Okay, so this was just to be sure that everybody was aware of what I was talking about, like case stability. And then to show that this thing is equivalent to I'm just looking at the then we have to go through filtration. Okay, so what I want to show is that that a test configuration is in one test configuration, integral test configuration, are in one-to-one correspondence with divisorial evaluation, actually dreaming one. Okay, so this is what I want to convince you about. Okay, so and for this I will go through a filtration, as I said. I don't know if you see well enough. Okay, so there's a theorem, or maybe a theory developed by Wittnystrom and Saidi, which says that finitely generated filtration of that ring are in one-to-one correspondence with a test configuration over XL. Okay, and so what do I mean by a finitely generated filtration? So maybe I cannot give as much detail. So for me, a filtration, or for this talk, this filtration will always be decreasing, left continuous. But I don't know. I don't think we will do so much details to use the left continuity, left continuous, separated or separating, and exhaustive. Okay, so decreasing, of course, it means that of course, decreasing means that they are included, like each part here is included in the in F prime for F lambda prime for lambda prime bigger. So separating, it means that actually F lambda greater, oops, maybe I should not try to go so fast, greater than 0, oops, I'm sorry, R is equal to 0 for lambda big enough, and that F lambda exhaustive means that F lambda R is equal to R for lambda small enough. Okay, and this is finitely generated. What does that mean? So it means that the graded CT, sorry, you see my calendar, Finitely, so it means that that thing, that graded CT algebra here is finitely generated. So that will be related to Dreamy, of course. And actually what we can do with that is that we can, the fact that it's finitely generated, it means that we can take the relative proj of that thing, and that will be this way, proj, and then that will be so maybe I can write it in n plus lambda in z. So I'm just copying what I wrote here, f lambda or m. So we can take the relative proj of that thing, and that will give us a projective variety over A1C. And actually, because of all this iteration we will get by the construction, by the relative proj construction, it comes with a C star action. Okay, so it's a test configuration. It is a test configuration, and that comes with some relatively ample line bundle. Okay, which is relatively ample. So here it's pi relatively ample. Okay, so conversely, given a test configuration, XL over XL, then we can construct. We get a filtration f lambda r. Now it's a k, which is given by h. So the global section of curly x of KL, sorry, over curly x. Actually, not quite. We take the weight decomposition of the C star action, and we take the one corresponding to the weight lambda, and then we restrict that to the first the fiber over 1. Okay, and so that gives a filtration of H0 X1 L1. Okay, so there's another way to define this filtration. What might be more easy to make a link with the evaluation is actually what you do is that if you have a test configuration, you have a section. You have a section over the line bundle, just over the first fiber, the fiber over 1, and then you can extend it C star invariantly over the old test configuration. That can give a meromorphic function, and then you have to see the order at 0. And this is why it will come. Okay. So now let's get back to the situation we are interested in. So with Dreamy Divergent, because for now I just recall what test configuration gives a finitely generated filtration, and the situation we are interested in is that given a divisional valuation, then actually we can consider that the filtration. Okay, so you get a filtration as soon as you have a valuation. Actually, you have a filtration, but the fact that it's a divisional variation will give us many things, and especially that if it's dreamy, because then we will be able to take the proj. Okay. And so the fact that maybe I should write it down. So the fact that F is dreamy will allow us to take the proj as we want, and that will be enough to because that filtration will be finitely generated. So it's better to write it this way. So it means that Fx R is finitely generated. Okay. So so what we prove is that whenever we have a filtration is induced by a dreamy divisor evaluation, the associated test configuration is enter. Okay. So actually it's so the proof is Fujita's proof. Just we realize that it's that it works perfectly well for in general, and so it's and I will give it because it's very simple and that gives the right idea. Okay, so from the Rees construction, so that gives you the different global section space of or coordinate rings of the fibers of the relative proj construction, then you know that H0 that the global section of L0n, which are the section you need to compute the asymptotic range, then it's given by these quotients, or x. Oh, there's two. There's here. It must be k, and here it's supposed to be k. Plus 1 or x. Okay. But in our case, because it's evaluation. Okay. In our case, that space, maybe I can take it more easy. Actually, here. So that thing, if I take off 0, this is exactly the sections vanishing exactly at order exactly x times. Okay, so maybe I will need more space. And then this is a very important for us. This is what we are using. Okay, so and this is crucial in the argument, because then if I call that thing is kx, just to simplify, okay, then if sigma then is kx without 0, or maybe I have to already put that without 0, okay, and tau is in SMY also without 0, then if you look at the product section, then it will vanish exactly x plus y time. Okay, and so it means that it's in there, x y plus y, so it's not 0. It's not 0, which proves that it's an integral domain, and this is what we needed to prove. Okay, so this is very pretty test proof. I don't say that just like it works for us as well. So, and that gives this is the observation that that is very important to understand this the statement in our main theorem. Okay, So so for the converse, so what this lemma proves is that given a dreamy divisional evaluation, then we get test configuration, which is an integral test configuration. And actually for the converse, it's just a particular case of Buxom, Hisamoto, Johnson result, and it's a very, they're a very big paper. Analyse de l'Institut Fourier is actually, so when we have a test configuration, if you remember the picture, then we can have many pieces over the in the integral fiber, and in case you have well, you can consider each of these pieces as a divisional evaluation over the original manifold. Well, that sounds very obvious, but it's not. Actually, for this, so of course, they are working with the dominating what test configuration that dominates, but actually it's not a big issue because you can always go back to that case, and it's not obvious to prove that this is. Maybe I can make a picture here to try to explain this. So if you have, if we have a test configuration, which is integral, okay, then there's a good chance that it does not dominate. So there's no, does not dominate the product, okay, but then you can take a resolution and then you will get another test configuration over X, okay. And the fact that it's integral here means that the test config, the central fiber here is the central fiber is an integral, right? So this is a irreducible and reduced divisor, so it's already something. And then you can take the strict transform here, okay. And then that, because and if you have a section over X here, if you have a section here over X, then you can lift it here, and that will give you a divisorial valuation. Okay. And so here I have to give more details. So here it's a 0 that didn't came in with, okay. So given an integral test configuration, there exists a divisional valuation and a number M, and the associated filtration is given essentially like what we have, okay. So here, what is M? So M will be, so if I call here, P, Q, P, then I have P star L minus Q star L, not curly. The first one is curly, and that gives a divisor, which is supporting on the central fiber, such that, and then we define the M that I use here as just the order of D over that section, that divisor. That irreducible and reduced divisor upstairs, okay. And so maybe there's too much color already. So here that's going to be the X in the valuation. We are in the filtration. We are looking from the divisional, well, from the perspective we had before with that F, okay. Okay, so so that gives most of the so if you leave me a few minutes more, I can just give the main idea how we compare the or at least how we use the MMP actually to compute the valuation. So is it okay?
Yes.
Yeah, fine. We've got 25 minutes till the next talk, so go for it.
Okay, so so from So from the filtration point of view, so when you have a filtration associated to a test configuration, then it's natural to try to compute the non-synthetic invariant from the data of the filtration. Okay, and actually, what has been proved by Wittgenstein, Heidi, Coxon, Samoto, Janssen is actually that you can do that very well with expressing the weight as something like that. So you have the weight, which is in some sense coming from the Rees construction, if you remember, and you also have the dimension, which is just here. So here I'm a little bit vague. So here you have sorry, what's happening? You have so here lambda runs in a bunch of numbers that I will call lambda k min, which is a standard notation, lambda k here max. Okay, because for each fixed k, then the space of section is finite dimensional, so the filtration will be finite. So it has to stop at some point and start at some point and stop at the other end. Okay, and so that is the these number, and actually things are very nice in algebraic geometry. So you can always rescale the line bundles, so to get rid of some problems. And so here, so if you rescaling, L if necessary, then we can assume that lambda k min or max is just equal to just k times lambda min or max. Okay. And what we can check is that if we have a filtration associated to F, then using this little using this, then we can get that lambda min, which is at the limit, is 0. Okay, and the maximum is just actually the pseudo-effective threshold that we already defined. Okay, so we know in some sense where it goes, and so that's very useful, because that will allow us to compute the non-synthetic invariant and the beta invariant in well, easily, not really easily, you will see. Okay, so but at first there's the first part, which is a bit easy, is that we can express the weight, which was just given upstairs, because if you see here, this is a telescopic sum. So we say that in French, but I don't know if you... So it means that many terms cancel each other, and then we are able to write it as minus k, the pseudo-effective threshold, the dimension of Rk plus Fk, right? Where here this function is just the sum over, let's say, lambda greater than 1, greater than or equal to 1, the dimension of the piece of the filtration here, okay? Which, using equivalent Riemann theorem in the way like Buxom, Pisamoto, Janssen proved, can be expressed as an asymptotic extension that you can write, that I would write this way. Yes, and OK n minus 1 Okay. And now it's not that easy, but well, that part is easy, just some kind of arithmetic, like very basic, to show that the Dawson-Asymptotic invariant in the setting will be given by that formula, and then we are left with trying to understand these two numbers. Okay, so but now comes the real problems, is that in general we cannot easily compute the volume. It's not something easy to compute, and so it's not that easy. Okay, so maybe I can remark. So whenever when x is smaller than the threshold, pseudo-effective threshold, then we know that L minus X F is big. But it's not, not in general, not necessarily ample, right? Okay, like it would be, so imagine for a second, just to simplify the problem, imagine that for all x in 0 strictly smaller than the pseudo-effective threshold, then L minus XF is ample. That's not true in general, right? It's in general not true. In general, not true. But imagine that it is, just to see the idea. Then we can use a variant of Fujita, Fujita's variant of asymptotic Riemann-Roch theorem to estimate these two numbers as follows. Okay, which, well, it's not completely crazy in the setting, because we have the sum of the dimension, and it is given via Riemann-Roch theorem kind as an intersection formula. Okay, so this is what we get. Okay, and assume that you can do that, then it will be just well, then from this you can just have to use in the formula, replace key y plus f. So because all these intersection formula, this is on y, and you want something, you want to have an invariant defined on x, so then you can replace it by ky plus axf, and this is why the log discrepancy appears in the formula. Actually, this is really there. Then some integration by part, and then you will get that essentially that the Dawson-Asymptotic invariant is beta f. Okay, essentially. Okay, so but here I'm using something which is clearly not true. Okay, which is that. So to bypass this, actually we did like Fujita did. We used that very big theorem of Kalugiros Lazik, which is kind of MMP theorem, saying that in our situation, and here I'm using that F dreamy to use this, I can actually split the interval 0 to tau f. I can split it into subinterval, and for which there's a birational model, such that the bundle I'm looking at I'm interested in is ample. Okay, and then we have to work a little bit some technical issues, but it's from there we have to work on these ample model, model with an ample bundle. And then we use again the Riemann-Roch formula in the sense of Fujita. So thanks a lot for your attention, and sorry I took more time.
Okay, thank you very much. Are there any questions? You can raise hands or just unmute yourself.
Can I ask you a question? First one. Hello.
Yes.
Oh yeah. So I was just checking if I'm muted or not. So your construction is very nice. The theorem, the correspondence is nice, especially for algebraic geometers. Most of us don't care so much about Kähler-Einstein, but the good thing that came out of K-stability is the moduli, K-moduli. I mean, did you explore that part for polarized varieties? What are the modular implications?
Well, I would say for my part, no. No, I didn't. Maybe Rui, I don't know if he's here. Maybe he did. But well, we proved some results concerning well, just reprove something that we knew, but from the but from the perspective of just like trying to understand a little bit more what the valuative stability is. To what extent I would be happy to, well, I believe it could be interesting, like for example, for a Thibaut Delcroix example, to see how it can be used in this setting. But I would say no. And I'm not an algebraic geometer, as I said. I just wanted to try to understand this valuative stability stuff. So I'm
very nice. It's already, I think it's very nice. Yeah. Another question is slightly technical. For some bizarre reason, some birational geometers like the delta more than beta.
Mm-hmm.
I don't think delta works immediately here, right?
The delta invariant, the preferred delta than beta invariant.
The computation, yeah.
Yeah. Actually, yes, we have some relation in some particular case between these alpha delta invariant and alpha invariant. But this is in some particular case, and we didn't. Maybe they actually, for one thing I could say about these questions is that, like, well, I think there are many things to do yet still, and then that would be and yeah, I think it's one thing which is nice about this result, I think, is I'm sorry, I'm not very modest saying that, but is that I feel that it opens the door at many more things, but this is just a start. And no, we didn't explore much, but we have some projects. But
okay. Cool. Thanks a lot.
Any other questions? In that case, let's thank Evelyn again.